Dear ladies and gentlemen, I'm welcoming you and thanking you all for joining our LOYTEC Support Tech Talk about the topic BACnet IP. This is our second edition in English. The previous one was about Modbus RTU. If you're interested into this event, then it can be rewatched under the following link. The purpose of this LSTT is to learn how to correctly set up and debug certain BACnet functionalities using our LOYTEC devices. To do so, we're going to use these additional software tools. The first one would be Wireshark, which can be downloaded under the following link. And the second one is called YAPE, which is an abbreviation for yet another BACnet Explorer, and it can be downloaded under this link. Let's continue with the contents of our BACnet IP LSTT today. Example number one is going to be about the network device identification process. Example number two, foreign device short FD functionality. Example number three, BACnet broadcast management device short BBMD functionality. Example number four, object instance numbers. And example number five, priority array. Example number one, network device identification process. For our first example, we're going to perform a BACnet network scan. This can be done by navigating to the folder imported, opening the context menu of BACnet network scan, and scan BACnet network. Now we're going to use the functionality discover devices. And the device with the instance number 17,850 is the device we're going to scan the objects from. And as visible here, the scan resulted in one warning. If the details are viewed, we're seeing that the device 17,850 is ambiguous. We are now going to find out what this exactly means and how this can be debugged. To further analyze the problem, we are now navigating to the BACnet statistics page on the web UI of our LOYTEC device. From here on, go to Statistics, BACnet, and then Ports to get the BACnet relevant information. Here you'll see some general informations like the used Ethernet port and the protocol, and also how many seconds ago these statistics have been cleared. Also in the general section you'll find the amount of packages which has been received and transmitted by the device. In the application layer message details, you will find, among other things, the amount of confirmed requests, unconfirmed requests, simple acknowledgements, and complex acknowledgements. Confirmed requests are directed at a specific device and need acknowledgement. Confirmed requests could be the services subscribe CUV, read and write property, ACK alarms, etc. Simple acknowledgement are answers by a remote station for services which need acknowledgement, like confirmed requests. Complex acknowledgement are also answers by a remote station but do already contain response to the requested data. For example, the confirmed service read property is requesting data, so the remote station only sends one complex acknowledgement in response, containing the requested data by the request. Unconfirmed requests are broadcasts, which do not need acknowledgement by the remote station. For example, I am, who is, who has, I have. Right now we are only interested on the counters I am and who is, as these are used in the BACnet device identification process. We will now take a look at how this mechanism works in a more detailed manner. Take a look at this network configuration. The broadcast address is 10.0.0.255, and if you now start a device scan on one of these BACnet devices, then a local broadcast with the service choice "Who is" will be sent to the broadcast address of the subnet. The broadcast message includes a property which defines the device instance number range, which shall be scanned. If one of the BACnet devices in the same subnet is configured to a device instance number contained in that range, then the device will also answer in broadcast with the service choice "I am." For example, device instance number 17,850 and 17,851. Continuing with our example, let's navigate back to the BACnet statistics page on our WebUI. In the tab Unconfirmed Requests by Service Choice, we can see that our device has sent 2 IAMs and has received 2 WHOIS. Since from that we cannot deduce the error from this information, we need to further analyze the issue. For this, we will need to analyze the network traffic to the device in detail. Our devices offer 2 possibilities on how to capture the traffic. The first one would be to create a local packet capture file. This can be done directly on the WebUI by navigating to Statistics and then Packet Capture. Depending on the used device, you will see X amount of available capture ports. Since we know our BACnet traffic is on Ethernet 1, we can simply press the Start button to enable capturing. There's also an additional possibility to filter the traffic. This is helpful in case there's a lot of traffic going on in the network. The log could then be stopped after a few minutes and downloaded directly to the hard disk by pressing the Download Capture Files button. The other possibility would be to use the remote packet capture functionality. We will not be using this today, but I will show you how to activate this functionality on our devices and how to configure Wireshark to use this remote packet capture function. The remote packet capture functionality can be activated on our LOYTEC devices by navigating to Config, Port Configuration, and then the used Ethernet port. In our case, it's Ethernet 1. And here, just activate the functionality by activating the checkbox. And I would also recommend to set up an authentication for security purposes. If you're done, simply press the Save Settings button. A restart of the device is not required. Switching to Wireshark, I will now show you some Wireshark basics which are important for a further analysis of the problem. How to set up a remote interface. From here on, the remote packet capture functionality can be configured in the following manner. Navigate to Capture, Options, then Manage Interfaces, Remote Interfaces, click the plus button, enter the host and the port, and input your credentials for the WebUI of our device. With this information, the Wireshark will be able to connect to the remote host. If this was successful, you will see the remote host here in the list, and then you can press the OK button. To start logging, simply click on the interface and click Start. How to filter packets according to our needs using the capture filter functionality in Wireshark. For example, if we're interested in only seeing BACnet packets, then simply put BACnet into the filter. Valid filter entries will turn the field green, whereas invalid ones will paint it red. If you want to filter a specific IP address, use ip.addr and specify the IP address. This will show all packets coming from the specified or are going to that specified IP address. To specify a certain packet direction of the IP address, replace the ADDR with either SRC for source or DSD for destination. Capture filters can also contain logical operators like AND, OR, NOT, and etc. So for example, this would be the OR operator. Now we're looking for either that IP address, destination, or any packets containing that IP address. If you want to specify a protocol, you can put an AND, for example, TCP. A yellow field means that the input is not clear. So in this case, it would be better to specify the search term, for example, like this. So either this IP address destination or the IP address and the protocol TCP together in one package. Decode packets. Wireshark identifies protocols among other things by the used port. So if your BACnet communication is on a different port than the default port, which is in hexadecimal 0xBAZ0 or in decimal 47808, then the packets will not be automatically decoded. In this case, you could identify your BACnet packet by filtering after the used UDP port. In my case, this is 47810, so I'm just putting the capturing filter udp.port and the port number. After doing so, then I will only see my BACnet packets, which are still not decoded correctly. To set the decoding correctly, open the context menu of the packet, select Decode As, make sure the field is correctly configured to UDP port and the value is 47810. Now on the current, open the drop-down menu and look for BVLC, which is an abbreviation for BACnet Virtual Link Control. Select the OK button, and now Wireshark is decoding the packet correctly as in BACnet packet. With these tips in mind, we should now be able to continue the debugging of our problem. I have manually downloaded a capture file from the WebUI of my LOYTEC device and opened the file with Wireshark. Now I'll set the capture filter to BACnet. What are we seeing here? In packet 422, we're seeing that a device with the IP address 10.12.11.21 is sending an unconfirmed request with the service choice who is. We can click on the packet and open the Building Automation and Control Network APDU. Here we see that the device instance range low limit is 0 and that the device instance range high limit is 2,097,152, which is the max allowed number. This request is answered by multiple devices in packet 423, 425, and 428 with the service choice IM. You can see the instance number which was being reported here, and we can actually see that two devices are sharing the same device instance number. With that provided information, we can actually already deduce the ambiguity problem. Two BACnet devices with a different IP address share the same BACnet device instance number. thus cannot be distinguished in a BACnet network. We have now finished analyzing example number 1 and can take appropriate actions to resolve this problem by changing the instance number of one of these devices. Example number 2. We are once again back to the links configurator. In the BACnet network scan dialog, you're trying to scan a certain device, but are not able to find the one you wish to read out. At first, I'd recommend checking if both devices are in the same network and share the same BACnet port. If it turns out that this is not the case, then there is still a possibility to configure the device as a foreign device, or to use multiple BBMDs in each subnet or port. See this illustration of the subject for a better understanding. Let us assume that our network consists of two different subnets. Subnet 1 with the range 10.0.0.0 and the broadcast address 10.0.0.255, and IP subnet 2 with the range 10.12.10.0 and the broadcast address 10.12.10.255. In IP subnet 1 we have an BBMD and multiple BACnet IP devices. In subnet 2 we have two BACnet IP devices. Assuming device A in subnet 2 wants to communicate to devices in subnet 1, then device A can be configured as a foreign device in order to allow itself to communicate to subnet 1 through the BBMD. After setting this up, device A will not be able to communicate to the device B in subnet 2 anymore. Which effect does the registration of a foreign device have to a BACnet broadcast management device? On BBMD-enabled LOYTEC devices, it's possible to view all devices which have registered themselves as a foreign device. This list can be found under Statistics, BACnet, and then Foreign Device table, FDT. Here you'll see all the list entries with the IP address, the configured BACnet port, and how long basically the registration is staying valid. Let us analyze the foreign device communication in Wireshark. I have once again already created a packet capture which has the foreign device registration process recorded. In the capture filter I will set up the following filter, BVLC, which allows us to see the foreign device registration process. It also includes the normal BACnet communication recognizable from the protocol type BACnet APDU. In packet 68 we can see that our device with the IP address 10.12.11.21, which we assume lies on the other subnet, in this case BACnet port, which is recognizable here from the source port and the destination port, is sending a request to the BBMD in the other network with the function register foreign device. Packet 69 is the answer from the BBMD to the request with the result successful completion. So this means that it's now possible for device A of subnet 2 to communicate to devices in subnet 1. We will analyze the BACnet communication from the point of view of device A in subnet 2. We know that an unconfirmed request is always sent as a broadcast to the broadcast address of the network. In case of foreign device, the whole BACnet communication to and from the device is routed through the BBMD. Let's see for example packet 1299, which contains an unconfirmed request with the service choice whois. Under BACnet virtual link control, you can see that this is a forwarded packet from the BBMD, recognizable because of the function forwarded npdu. It also contains the IP address from where this request is coming from. In packet 1301, we can see the IM answer coming from our foreign device. Even though it's an unconfirmed request, it's directly sent to the BBMD because of the FD registration. packet 1302 and 1304 are forwarded IMs forwarded from the BBMT to our foreign device. These are some other BACnet devices in the other subnet. Example number 3. Up to this point, we've learned that broadcasts are propagated only subnet or port-wide because IP routers normally filter out broadcasts. But what if we have multiple BACnet IP devices in multiple subnets that need to communicate with each other? The solution for that would be the usage of one BBMD per subnet. Let us also assume in this example that our network consists of two different subnets. Subnet 1 with the range 10.0.0.0 and the broadcast IP address 10.0.0.255, and subnet 2 with the range 10.12.10.0 and the broadcast IP address 10.12.10.255. In both subnet 1 and subnet 2, we each have one BBMD and three BACnet IP devices. In order to enable the communication between both BBMDs, we need to set up a BDT, which is a broadcast distribution table. The BBMD functionality in LOYTEC devices can be activated via the web UI under Configuration, Port Configuration, the used Ethernet port, BACnet IP, and setting the BACnet IP mode to Broadcast Management Device. Simply save settings and restart the device if needed to. To finalize enabling the communication between the two BBMDs, the so-called BDT, which is a broadcast distribution table, needs to be filled out. This table can be edited via the web UI by going to Configuration, BACnet, and choosing BDT from here. Simply add the other BBMD with its IP address and the corresponding port by pushing the Add Device button. Input the IP address, the port, which can be left at that, and press Save. Now to simply distribute this broadcast distribution table, we can use the Distribute button. So we do not need to manually add the list members if we have more than one device. Just push the button. So I'll now switch to the other BBMD, which runs on another BACnet port, and we'll check the BDT table if the entry has been added successfully. And as you can see, it has been added successfully. Let us analyze the BBMD communication in Wireshark. I have once again already created a packet capture, which has the BBMD registration process recorded. I'm going to use the capture filter BVLC or BACnet, which is needed to display the distribution of the BVLC function write broadcast distribution table. If you open the details of the packet 222, you will see under BACnet virtual link control that the BDT was distributed to BBMD1 with the IP address 10.12.11.22 and the port 47809. Also to the second BBMD with the IP address 10.12.11.23 and the port 47808. If this registration was successful, like we'll see in packet 224, then we'll see that the result of this function is successful completion. The communication between both BBMDs is now transparent BACnet-wise. So now looking at the communication in Wireshark, we have the following setup. We have BBMD1 with the IP address 10.12.11.22, which is configured on the port 47809, and BBMD BBMD2 with the IP address 10.12.11.23 on port 47,808. For example, let's now look at packet 606. We have a device with the IP address 10.12.11.20, which is communicating on the port 47,809. The device is sending an unconfirmed request with the service choice whois to the broadcast IP address of the subnet. Now the BBMD, which is configured to this subnet, which is the BBMD1 with the port 47,809, is forwarding this whois request to the other BBMD with the IP address 10.12.11.23 on port 47,808. This BBMD number 2 is then also broadcasting the same message to the broadcast IP address of the subnet, but for the port 47,808. This means BACnet IP devices, which are now answering with the service choice IM on the port 47,808, are sending their request to the broadcast address as per standard. BBMD number 2 then is forwarding these packets to BBMD number 1, thus enabling the communication between these two subnets, or in this case, ports. Like seen here in packet 612, the IM is being forwarded, and this forwarded message is then broadcasted on this port 47,809 by BBMD number 1. Example number 4. In this example, we'll assume that we integrated our BACnet data points onto a controller via an IDE file. On our LOYTEC WebWire BACnet commissioning page, we're seeing that the other controller is online and isn't also displaying any other error messages. The problem is that if you view the data points on the BACnet port, that one of these data points is offline. What could be the problem? This example will show how this kind of error can be analyzed with the help of Wireshark. Before analyzing the problem, let's see how the data of BACnet objects can be retrieved. BACnet actually offers multiple possibilities on how data can be accessed from another BACnet device. Either the properties, like in this case present value, is being subscribed via COV, which means change of value. So as soon as the server object or client mapping changes its value, the counterpart is being COV notified and also sent the value. If an server device is not supporting COV subscriptions, then the client mappings can also be polled in a specified interval. The behavior on how data is obtained can either be configured automatically. This means our firmware checks if the COV subscription is possible. If not, then it will be polled. Or it can also be manually configured inside the links configurator by selecting data point, all properties, client map type. To continue the analysis, we will once again start a BACnet packet capture. And we have to make sure that a polling event is being sent to the other device so we can hopefully find the error. This can be done by navigating directly to the data point, which is located on the BACnet port, and then data points, the device, and choosing the data point we wish to access. Now to manually retrieve, so poll and value, we can use this cloud symbol and it will actually trigger a poll from the network. After doing so, let us stop the packet capture and we'll analyze it once again with Wireshark. To filter out the unwanted traffic from Wireshark, we can once again set our capturing filters. Wireshark actually offers a wide variety of available filters for different purposes and protocols. I've compiled a list of important filters for analyzing BACnet communication for you. Setting the filters manually is not the only option Wireshark offers. Another possibility to set and capture filter is by directly selecting from the context menu. Simply search after a packet of your choice. For example, we can take packet 432, open the details, the Building Automation and Control Network APDU, and for example, if you want to filter after the service choice subscribe COV property, open the context menu and select Apply as Filter. For example, Selected. This will replace the whole capture filter with the following entry. In this context, the capture filters can also be combined with a logical expression. For example, if you want to include the object identifier, the instance number to the capture filter, we open the context menu, apply as a filter, and we can select from here whether it should be with a not or combined with an and or not or not selection. For example, now after using and selected, we're having the first capture filter in this field and the second one, which is the instance number, here, and they are both logically combined with an and. Let us return to our example. For example, relevant is the last entry of the table. This allows to filter out after the instance number of the BACnet object. But where to find the instance number of the BACnet? This can be done via the web UI by navigating directly to the data point once again, which is located here under the BACnet port, data points, device name, and by clicking on it. And here is the object type and the instance number. So now we are switching to Wireshark and putting in the capture filter, which is this one, and we'll set it to 176. From this point, we have two possibilities where this problem can be analyzed from. Either we check the subscription, the subscribe COV confirmed request. The problem here is that we do not see the answer to that subscribe COV request, since the answer doesn't seem to include the object's instance number. So in this case, you could either just simply mark the packet and then remove the filter. Then we'll see here the answer. Or we could also use this invoke ID, which is unique in a BACnet communication channel. This can be done by simply setting it here, invoke ID, apply as a filter, and to replace the filter, use selected. Then we'll also see here the answer to that subscription request. And we could also check the manual poll request, which you can see here with the service choice read property multiple. So here we have in the object identifier the object type, which is analog input, and the instance number. This here is the confirmed request, and here the complex acknowledgement. Under a list of results, you get the result. You can also use here to collapse these. And here we can actually already see the property identifier, which is present value, reports and property access error. And if we expand this one, we can see the error class refers to the object itself, and the error code is unknown object. So this simply means that this BACnet object with the instance number doesn't exist on the interface of the BACnet controller. Example number 5. Commandable BACnet server objects implement a so-called priority array for the property present value. This array consists of 16 entries, whereas 1 is the highest entry and 16 the lowest one. A value which has been written on a higher priority overrules any value which is written on any of the lower priorities. Values on the priority array can be relinquished. This will result in the next available lower priority to be valid again. Priorities do not need to be relinquished to be assigned a new value. For this example, I've created a commandable BACnet server object, which is found under the BACnet port data points analog 0. In the native info of this details page, you will find the server object name, the object type, which is analog value, and the instance number 0. And the 10 refers to the present value, which it currently holds. Beneath that object and instance number and so on, you will find the priority array. On the leftmost, you will have the highest priority, which is 1, and on the rightmost, you will have priority 16, which is the lowest. The number behind the line refers to the relinquished default value. If all priorities are relinquished, then this default value will come into place. So for example, there's a value which has been written to the priority number 16, which is the value 15. You will see that the present value will change to that value. And if now a higher priority is being written, for example, priority number 10 with the value 5, then the present value will take that value, and priority number 1 with this value, and so on. So if that value on priority number 1 is being relinquished, then priority number 10 will come into effect again, as you can see here. If now also these priorities are all relinquished, then the relinquished default will come into place again. And this is how the priority array works. Hint: if you're not able to view a BACnet priority array on a third-party BACnet controller, then you could also possibly use YAPE. With this tool, you are able to view the priority array of a commandable BACnet server object. I'll not explain in detail how to use that tool. Please refer to YAPE's user manual for additional information. At first, we'll need to define the interface, which can be done by pressing the Add Device symbol. Here, choose your local Ethernet port with the IP address and the BACnet port you wish to listen and write to. Click on Add, and it will automatically send an whois to see which devices are reachable. So in our case, we want to read out this device, and the analog value 0 can be selected here in the address space. After selecting it, you will now see the properties popping up. One of these properties is the property priority. You can simply expand this list to see all the written priorities. So the one on the top would be priority 1, and the one at the bottom would be priority number 16. This is now the end of the presentation part, and I'm welcoming you all to our discussion. Feel free to ask any questions or wish to share one of your experiences regarding BACnet IP.